Part A of the problem asks you to find the domain of the function. To find the domain of a function with a variable in the denominator, you must set the bottom equal to 0 and exclude the x value when you solve the equation. So the first step will be to set the square root of x squared minus 4 to 0, and then work to solve for x. And so to remove the radical sign from the left side of the equation, we will square both sides. This will remove the radical sign and leave the other side of the equation unchanged, and 0 times itself is 0. We will then isolate the variable by adding 4 to both sides of the equation, and to find the value of x, we will take the square roots of both sides, and since we are inserting the square roots ourselves, it is understood that it will yield both a positive and a negative root. So when finding the domain of a fractional function, you must exclude all the x values that make the denominator equal to 0, because you can never divide by 0, meaning the domain of the function is all real numbers except 2 and negative 2. To write the domain in the proper notation, use parentheses to indicate the numbers not included. Use U, meaning union, to connect parts that are separated by a gap. Part B of the problem asks you to write an equation for each vertical asymptote to the graph of f. To do so, we need to look back at part A. Since we cannot have a 0 in the denominator, we cannot have x equals 2 or x equals minus 2 in the domain. The vertical asymptote tells us where the graph cannot go, so the vertical asymptotes will be the values x equals 2 and x equals negative 2. So limits can also be applied at this point in the problem. So as the limit of x approaches 2 of the function, that will give you a value equal to 2 over 0, and whenever a value is being divided by 0, it is indicative of a vertical asymptote. And this same concept will be seen as the limit of x approaches negative 2 of the function. Where the value will be equal to a negative 2 over 0. But both concepts tie in together, where if it's a number over 0, that'll give you the vertical asymptote when being solved in the limit. So part C of the problem asks you to write an equation for each horizontal asymptote to the graph of f. The horizontal asymptote for a function is a horizontal line that the graph of the function approaches as x approaches infinity and negative infinity. Because the asymptotes are defined in this way, it should come as no surprise that limits make an appearance. The horizontal asymptote of the function can then be solved for by looking at the limit of x as it approaches positive or negative infinity. And when solving for this, the negative 4 in the numerator is not really relevant because it does not have an impact on the function's end behavior. So we may just focus on the x values as the limits approach positive infinity and negative infinity. So since the degrees of the x values on the top matches the degree on the bottom, we will focus on just the coefficients of each, and as the coefficients of all terms here is 1, in both cases the value divided by each other will also be 1, meaning as the limit of x approaches positive infinity of the function, the y values of the function will approach 1. As the limit of x approaches negative infinity, however, the y values of the function will approach negative 1. And to explain that, it will be helpful to conceptualize this by plugging in a negative infinity into the function, and a negative infinity over the square root of negative infinity squared, that will give you negative infinity over the square root of positive infinity, which will then equal to negative infinity over positive infinity, which yields a negative value. And that is why, as the limit approaches negative infinity, the horizontal asymptote, is -1. And as it approaches positive infinity, it is 1. So part 2 of the problem asks us to find the derivative of the function. And to do so, we will begin by rewriting the original function to remove the radical sign. And so instead of it being x squared minus 4, taking the square root of x squared minus 4 in the denominator, we instead will have x squared minus 4 to the power of 1/2. So to solve for the derivative, we will use the quotient rule. So the derivative will read as follows. The derivative of f(1) times g, x squared minus 4 to the power of 1/2, minus the derivative of g, solved for by the quotient rule. So 1/2 times the inside left untouched, x squared minus 4 times the derivative of minus 1 times the derivative of the inside, 2x, times f, which is just x, all over g squared. So x squared minus 4 to the power of 1/2 squared. To solve for the derivative, you must then continue to simplify this. So first of all, we will combine terms as much as possible. So multiply the 1 by the x squared minus 4 to the power of 1/2, and the 1/2 by 2x by x. And also clean up the bottom. So instead of x squared minus 4 to the power of 1/2 squared, just leave that as x squared minus 4. So since there cannot be any term to the power of a negative exponent in the numerator, we then throw that down to the denominator. And so then we will have a fraction over a fraction, so it's key that we clean that up in the numerator and we find a common denominator for the terms, leaving us with x squared minus 4 minus x squared over x squared minus 4 to the power of 1/2, because that was the common denominator solved for. So you can see that you can get rid of both 1/2s and then multiply by the flipped x squared minus 4 under 1. That then gives us -4 over x squared minus 4 to the power of 3/2. Looking at the graph of the original function and the derivative can then help you see for all the concepts that we solved for.